Oh, imagine you're standing in a room in a house, and you want to know how long on average until I reach the kitchen. No, you wander randomly between rooms. The first passage time is the expected time until you reach the target for the first time. In a continuous time Markov chain, the idea is built from two components, the residence time in a state and the jump probabilities out of it. The residence time in state K is exponentially distributed with mean 1 over capital lambda K, the sum of all outgoing rates. This is when you leave K, you go to neighbor J with probability lambda Kj over capital lambda K. This is the relative weight of that particular exit. Combining these gives the central recursion, expected time in K, plus the probability weighted sum of times from the next state. And the boundary condition, t for the target state, is 0. If you're already there, no time is needed. Consider a Markov chain where the forward rates are 10 and the backward rates are 20, except from 1 to 0, which is 10. We seek the time from an empty system until the system first has two customers. This is step 1. Identify the target. State 2 is the target, so T2 is 0. We only need to find T0 and T1. Step 2. From state 0, there is only one exit to 1 with rate 10. The residence time is 1/10, and afterward we are guaranteed to be in state 1. And step 3. From state 1 we go to 0 or to 2, both with rate 10. Capital lambda 1 is 20, so the residence time is 1/20th, and we go to each neighbor with probability 1/2. Now note the crucial detail. With 50% probability, we fall back to 0 and must start over. That is why T0 is longer than just the residence times. Step 4. Solve the system. Substitute T1 into the equation for T0 and add a T-check. The pure residence times are 1/10 plus 1/20th, that is 0.15. Our answer 0.3 is twice as large, which makes sense because on average we must wander back and forth. In summary, we get one equation per non-target state, the boundary condition locks the system, and the Markov property lets us condense infinitely many possible paths into a finite linear system. And this is a powerful technique that complements equilibrium analysis and lets us answer questions about transient dynamics in queuing systems.